Here's a summary of what you should read on page 141. If you haven't read page 141, please do that first before watching this lesson. Let's summarize what page 141 says. First of all, it talks about the principle of conservation of energy. What that says is that there's always the same amount of energy within a closed system, and the energy can change forms, but the total amount doesn't change. In other words, energy cannot be created from nothing, and energy is not destroyed. It doesn't disappear, and it doesn't appear out of nowhere. Energy can change forms, however. When we talk about work being done on an object by a force, the force from one object on another object, both of those objects must be included in our closed system. Another important idea from page 141 is the idea of kinetic energy, sometimes called energy of motion. Things that have motion have kinetic energy, and the amount of energy is equal to 1/2 times the mass times the velocity squared. So for example, if I throw a ball that has a mass of 1 kilogram and it's traveling 4 meters per second, 1/2 times the mass times the velocity squared gives me 8 joules is the units that we use for energy. And you can see here it is the same thing, or it is the name we give to the unit of kilogram meter squared per second squared. If you accelerate an object to a greater speed by applying a force to the object, you increase the kinetic energy, K, of the object. Similarly, if you decelerate the object to a lesser speed by applying a force, you decrease the kinetic energy of the object. We account for these changes in kinetic energy by saying that your force has transferred energy to the object from yourself, or from the object to yourself. In such a transfer of energy via a force, work, W, is said to be done on the object by the force. More formally, we define work as the following. Work, W, is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. And the units of work are the same as the units of energy, joules. Don't get confused by the traditional meaning of the word work. In the physics definition, work is only done if there is a displacement involved. If you pushed on a wall all day until you're hot and sweaty, in the end, you've done no work because the wall hasn't moved. Let's develop an expression for work, and let's use a constant force to do that work. We know that a force causes acceleration, so let's let the x direction be the direction of the displacement, and we know from using equations of motion that we work separately in the x and the y directions. So an acceleration in the x is caused by a force in the x. Even if the force has a component in the y, that does no acceleration in the x. Okay, so if we're using a constant force, that means we can use our equations of motion because we have constant acceleration, and we'll use this equation. We'll solve this equation for acceleration, and we'll take what we get for solving for acceleration and plug it in for A in Newton's second law. We'll expand that and rearrange it, and we see that F times D is equal to 1/2 mv final squared minus 1/2 mv initial squared. You'll recognize these terms, 1/2 mv squared, as kinetic energy. So this term here is the final kinetic energy, and this term here is the initial kinetic energy. So the difference in those two is the change in kinetic energy. And we know that is work. And the work is achieved by applying a force over some distance. Let's look at an example. How much work is done on this 4 kilogram block as it moves through a certain distance? Well, the first thing we want to do is figure out what's the acceleration of the system, and to do that we need to draw a force diagram. So there we have it. the weight of the 4 kilogram block, the normal force on the 4 kilogram block, and the tension in the string, and the weight of the 10 kilogram block is going to accelerate the system. So let's apply Newton's second law to figure out the acceleration. The sum of the forces in the x is equal to mass times acceleration in the x, and here we're going to let the tabletop be the x direction, and the pulley changes that direction of force so that we can say the 10 kilogram mass is also moving in the x direction. Here's my coordinate system here. So T, if I look at this whole thing as a single system, the tension in the string is an internal force. So one of them points in the positive direction, one of them points in the negative direction, so they cancel each other out, as we expect with internal forces. Then the weight of the 10 kilogram block is the only force now in the x direction, because we have said up here that this surface is frictionless. And then that force is accelerating how much mass? Well, both blocks, m1 plus m2. So solving that equation for A, we see that the acceleration of this system is going to be 7 meters per second squared. Okay, now that we know that the acceleration is 7 meters per second squared, let's find out what the tension is in the string is. So to do that, we have to apply Newton's second law to either of the blocks individually, so that tension is an external force. And I show here the solution for solving it using either block. If I use the first block, the tension is the force that accelerates 4 kilograms at 7 meters per second squared, and that tells me the tension is 28 newtons. Or I could have looked at this 10 kilogram block. It has two forces acting on it in the x direction. Its weight in the positive direction, the tension in the negative direction, and those sum of forces act to accelerate mass number 2, which is 10 kilograms at 7 meters per second squared. And so using block 2, I arrive at the same answer, that the tension is 28 newtons in the string. So, how much work is done on the 4 kilogram block as it moves through a distance of 3 meters? So, first I'm going to calculate how fast is it moving. So here's my calculations. I know it's a constant tension, so it's constant acceleration. I can use my equations of motion. The block starts from rest. Its acceleration is 7 meters per second squared, and the displacement is 3 meters. Solving for the velocity, I see that when it reaches this point, after moving 3 meters, it will be traveling at the square root of 42 meters per second. Now that we know how fast it's moving at this spot, we can calculate what is its change in kinetic energy from here to here. So our change in kinetic energy, delta KE, is the final kinetic energy minus the initial kinetic energy. We know it started here at rest, so this initial kinetic energy term is 0. And we saw that at this location, it is now moving at the square root of 42 meters per second. So I plug that in for velocity. The mass is 4. I work out the math, and I see that it is 84 joules difference now of kinetic energy. The block has gained 84 joules of kinetic energy. Positive work has been done on this block by the tension. Now let's see, does that agree with our new expression for work, that work is equal to force times distance? Well, the force pulling on the block is the tension in the string. It's 28 newtons, and the displacement was 3 meters, and 28 times 3 is 84. So yes, it does agree with our expression for work, does agree with the old way we would have done it before we knew how to use this expression. This is how we would have had to calculate the change in kinetic energy. Now we have a simpler way of doing it. Force times distance. Notice also that units of force is newtons, units of distance is meters, so a newton meter is the same thing as a joule. Remember, work and energy have the same units, joules.